Direct from the Six, world-renowned, Canada's largest city, with Canada's biggest thinkers, visionaries, and hustlers. This is Startup Talk, featuring the founders, funders, innovators, and community leaders who've led Canada's startup ecosystem right here in Toronto. You'll hear the challenges, the failures, the successes. Toronto's Startup Podcast gives you the full story direct from the entrepreneurs and influencers who've made a difference. Now, the host of Startup Talk, the founder of TorontoStarts, the Startup Coach.
One thing was interesting is we are very deep in the cutting-edge research, is that current large language model, there's a lot of hallucination problem. And that's actually what we are working very hard to solve that ourselves. That's what we call large quantitative model. And if you're interested, I can elaborate more about how do we actually see about embedding the physical phenomenon of the laws of physics into the language model. That's what we're working on right now for the home building industry.
Yes, I would love, let's drill down on that in a bit. So you're calling it's not a large language model, you're calling it again, what?
A large quantitative model.
Quantitative model. And to reduce the hallucinations, you're putting physics into this model?
Yeah, so it's the cutting edge challenge is actually how do we make it has reasoning capability? How do you bound the constraint into the system to say it has to follow this rule? I'll use an example. In the Newtonian physics, right? So the second law of motion, we know that F equals ma, which like the Newtonian discovery actually set the foundation of modern physics world, leading to all this great discovery. And the second law of motion says the force equals mass multiplied by acceleration, meaning something moving, you have to apply the force to get it going, or you have to apply the force to make it stop. Sounds trivial and obvious today, but for the last 10,000 years of history of mankind, this is only found 400 years ago. So it's not that far away if you look at the time horizon. The second thing is actually not trivial, is that for Newton to understand this acceleration, he had to invent calculus to do that. So if you think about LLM, large language model, it's almost like the new invention of calculus. So that's actually tremendously powerful, so that we can discover those new phenomena. But one challenge in large language model is that it does not understand the causal relationship, meaning you can easily just mathematically change the formula to say, well, you know what, if I can increase the force or reduce the acceleration purely by just looking at math, I can change the mass, because mass equals F divided by A, right? So, if I give more mass without changing the acceleration, if I give more forces without changing acceleration, then the thing will get heavier. That for human is nonsense, but from a mathematical standpoint, a large language model do not understand it. It's actually as far as the causal relationship to the acceleration. So that's actually what we're working very hard to actually think about deploying large language model to a industry that actually moving dirt, building houses in a physical environment that you are governed by the laws of physics. And that's where we realize that we basically need to teach your algorithm that mass is something that you do not change. It's the force that causes the acceleration to change. And that's actually, those are phenomena we basically need to feed into the language model before and after, and actually have this physical laws of physics bounding the large language model to make it applicable for this industry. And that's actually got us very excited about how do we also be part of advancing the technology development as well.
It sounds very interesting. You know, when you're training large language models, oftentimes you're feeding in a scenario and then a solution, a correct solution, a wrong solution, whatever, on these tables to train it. How do you train it to understand that this formula equals the amount of physical dirt you have to move? Like, it's a thing that's a leap, for lack of a...
Yeah, so that's actually, of course, like we do not have, unlike OpenAI or Anthropic, we don't have billions of dollars to spend to build our foundation model. We basically take advantage of existing large language model, also taking some open source model. And what is open source model, by absorbing the data from the internet in their latent feature, essentially they build a understanding or abstraction of the world. So that allow it actually to create new solution in inference time. So of course, when we feed data into it, we feed data by providing some, like, for example, like we say, hey, math is something you cannot change. We feed those into the model. But then when it's coming out, we then deploy tons of classical machine learning approach, layer on top of that to basically do optimization theory. So there's a field that is actually not typically, you can put it as part of AI, some people might not. There's a field is actually called operational research. It's how do you minimize or maximize the objective function, like basically, for example, minimize the cost or maximize the profit of the business or maximize the utility of a resource with constraint. And those constraints are the physical law, the laws of physics. And also, when there are uncertainty, how do we play out to know if this situation, what would happen, if the other situation, what would happen, when we're making decision under uncertainty, we use a lot of multi-cloud simulation technique, which involve a larger volume compute, but very different compute compared to LLM. So we do a lot of things before and after by basically wrapping large language model. But on top of that, we just not just wrapping it, we put layers of more classical machine learning model that actually injecting the physical phenomena into the technology to help them to make better decisions.
And here's another question. Just again, I'm looking on the outside coming in mind. When you say math doesn't change, I don't know if that's actually true. And when I say that, I'll explain that in a second. You're looking at a scenario, you say, I got to move this volume of dirt. Okay.
Yeah.
If it's clay, the mass might be different. If it's wet dirt, the mass might be different. If it's dry dirt, it might be different. So how do you explain that to, say, a computer AI model? Because the math actually doesn't change, but the environment changes enough that the formula math actually changes because of it.
Oh, absolutely. I was more referring to that analogy, more like, for example, you can say, hey, like, you can make a demand prediction, but the demand doesn't go negative. For example, but the mathematics would say, allow you to put negative. You basically now put boundary into the math model, but that actually all of a sudden, it's more like in math now is not a continuous function. So that causes a lot of math just immediate breakdown. So your question is, how do you feed that in? Is basically, that's where it's actually in the post-processing of the language model after you actually extract it out. So in input, we basically say, these are the phenomena that you have to be grounded in the input. In the training data set, we actually also do a ton of feature engineering to basically bias the data intentionally to certain distribution. That's actually in the early days of the RGFL technique for large language model. How do they train? It's almost like, I'm going to use another analogy to explain it. The internet might have a lot of cat information, a lot of cute cats. But if you want to ask a large language model, what's the most common picture you will see in the world, they might spit out as cat. So how do you actually correct that? Is actually you rebias those information back to the phenomenon is governed by the laws of physics. So that's in the input phase. But on the output, then when the outcomes actually bridge beyond those laws of physics, we basically then kick in other machine learning technique to say, well, that's the outcome that we're going to reject. There's a lot of governance, there's a lot of guidance, there's a lot of checks and balance around those to basically eliminate the obvious problem. And then the second layer is now we deploy simulation to understand the sensitivity exposure of such decision. How much risk are we actually talking about? So it's getting a bit more deeper in the mathematics, but it's before and after you basically put those rules and balance and policy around it, so they make the right decision for people.
I'm always fascinated about, how this is done and how different companies are training AI and this large quantitative model versus, say, small language models and large language models, and how everyone's having a different approach, and now large action models that are out there. It's really nice to see, how all these agents and things are coming into play. So where can our listeners go and find out more about Openhouse.ai and your work, Will?
Oh, it's simple. It's just go to our website, Openhouse.ai, or look at us up in LinkedIn. I know our team is actually constantly pushing even our latest research and what we have been doing, helping our client. yeah, so Openhouse.ai, that's the website.
Yeah, and the links will be in the podcast show notes for anybody listening. And we'd like to leave our audience with one actionable tip with our entrepreneurial audience you'd like to leave with thought.
I guess just if you are coming more from my own experience, I was working in big corporation, head of R&D for, different public company. If you are one of those, you might say, hey, I actually want to do something different, but constrained by big corporation policies. And sometimes just give it a try and take a leap of faith and you will figure it out.
Great advice. Take a leap of faith. I really appreciate you taking the time to talk to us about Open House AI and the work you're doing and some of the advances in the AI field I hadn't even knew about before today. This has been a great discussion.
Thank you. Thank you for having me.
Thanks for everyone listening and watching.
This has been Startup Talk, Toronto's startup podcast. For more exclusive content, the episode vault, and to be part of TorontoStarts community, visit TorontoStarts.com. Get your name on the newsletter mailing list and check out our upcoming events. For more episodes, subscribe now. And please recognize the time and work behind the scenes put into connecting you with the biggest visionaries, entrepreneurs, and innovators in Toronto by leaving a 5-star review. Join us for more next episode from Toronto's most active entrepreneur and startup community on Startup Talk.